So, we have seen how oxidation is occurring and how reduction is occurring, and also we said that there is an energy or electricity is developed in a Daniell cell. Now, how does this energy develop, or why do we say there is flow of current? Now, the flow of current can occur only when there is a potential difference, only when there is a potential difference. That means, at each of the electrode there is going to be a development of potential, which you call it as electrode potential, which is called as electrode potential. So, what is an electrode? Electrode is nothing but a metal piece which is in contact, a metal piece M which is in contact with a solution containing the ions of containing its ions. Now, so there is a separation between, or there is a separation between the surface of the metal and the solution, and because of this barrier there is a development of electrostatic potential. Electrostatic potential, which in this case we call it as the electrode potential, which we call it as electrode potential. Now, all the metals cannot have the same electrode potentials, or they will not have the same electrode potentials. Different metals have different electrode potentials, and for that purpose, and so for us to compare the electrode potentials of the various metals, we have to maintain a certain conditions. So, if we maintain, what are the conditions which we can maintain? We can maintain the concentration of the solutions and the temperature. So, if you measure the potentials at 25 degrees centigrade or 298 Kelvin, and the concentration of the metal ions is 1 molar, then the potential of the electrode is called as the standard electrode potential, which is represented by E naught, So, now I would like to discuss how these electrode potentials, how the electrode or the potential at the electrodes are developed, or how you have the potential developing at the electrodes. Now, whenever we place a metal into its own solution, these metals have a tendency to pass into the solution as its ions, or you will have the reaction occurring Mn, giving Mn plus Ne minus. Now, what is the force which is responsible for the metals to go into the solution as its ions is called as the solution pressure. It is called as the solution pressure, and this is the solution pressure which is responsible for the metal atoms to get converted into the metal ions and pass into solution, and this process is called as the dissolution process. It is called as the dissolution process. On the other hand, the metal ions which are in solution, they also have the tendency to get converted into the metal atoms and get deposited So, you have the reverse reaction can also occur, giving M. And what is responsible for this? What force is responsible for the second reaction to occur? That force which is responsible for this reaction is called as the osmotic pressure. It is called as the osmotic pressure, and this process is called as the deposition process. It is called as the deposition process. So, in when you place a metal in its solution, then there are two forces. One is the solution pressure and the other is a osmotic pressure. So, the difference between these two properties leads to the development of the electrode potential, or there is a competition between the dissolution process and the deposition process, and that competition is responsible for the development of the potential at the electrodes. Now, let us see how a positive electrode is obtained, or how an electrode will attain a positive charge, and how the electrode will attain a negative charge. So, for this I will take zinc as an example, what we have seen in our galvanic cell. So, when we take zinc, we have said that zinc in the galvanic cell acts like the anode, and it is negatively charged. So, if I take a zinc electrode, this would be zinc metal which is placed in zinc sulphate solution. So, zinc metal is going to be in contact with the Zn2 plus ions. So, in this case, again here there will be there are going to be two reactions. What are the two reactions? Zn is going to give Zn2 plus 2E minus. What is responsible for this? Osmotic pressure, and there is going to be deposition of Zn2 plus ions due to, this is solution pressure, and the deposition of the zinc ions due to osmotic pressure. So, in the case of zinc, due to the nature of the metal, the solution pressure is going to be higher than the osmotic pressure, and hence the first reaction is favored, or the dissolution process is favored, or Zn gets converted into Zn2 plus ions, and then it gets dissolved in the solution. So, what is going to happen here? And in that case, here you have the electrons. So, you have on the surface, you have the accumulation of negative charges. Now, to balance these negative charges, the positive ions which are in solution will move towards the electrode, This leads to the development of the electrical double layer. If there is an electrical double layer, definitely there is going to be a development of potential, and that potential is what you call it as the electrode potential. Now, because there is accumulation of the negative charges, the zinc electrode will have a negative charge. It will have a negative charge. So, in an electrochemical cell, the anode, why is zinc the anode? It is the anode because it is undergoing oxidation, and the anode is going to be a negatively charged, or any negatively charged electrode in an electrochemical cell, you call it as the anode. So, this is a negative electrode. But what about the case of copper? What happens in the case of copper? Now, here you have copper. You have copper metal, which is placed in Cu2 plus solution, placed in Cu2 plus solution. Now, even in this case, they will due to the solution pressure, Cu will go into solution Cu2 plus 2E minus, and due to osmotic pressure, Cu2 plus 2E minus can get converted to Cu, But because of nature of copper, because of nature of copper, the second reaction is faster. So, therefore, copper ions get reduced to form the Cu plus atoms, or reduction is going to occur at the copper electrode. So, because of that, you are going to have a depletion, you will have positive charges on the, surface, because the electrons are being used up, and the negative ions from the solution will come on to the surface to neutralize that, and hence copper develops a positive charge. So, therefore, copper is going to be the positive electrode, and since reduction is occurring here, this is going to be the cathode. And because of the separation of the charges, there is again a development of electrical double layer, and that leads to the development of a potential, which you call it as the standard electrode potential. Now, since here the potential which is going to be developed, because oxidation is occurring here, you say this is the oxidation potential, and since reduction is occurring here, you call this electrode potential as the reduction electrode potential. Now, if you want to calculate the oxidation potential of reduction potential of zinc, the value is going to be the same, only the sign of the potential is going to change. If similarly, if you want to calculate the oxidation potential of copper, this is whatever we obtain is going to be the reduction potential, and if you want the oxidation potential, then you just have to reverse the sign, but the value is going to remain the same. Now, here we have said that, we have seen that in the Daniell cell, when we are measuring the potential of the cell. What is a cell? A cell is an arrangement which contains both the anode and the cathode. But if I take individually the zinc, this is called as the oxidation half cell, and this is called as the reduction half cell. If I want to measure just the electrode potential of zinc or only the electrode potential of copper, I cannot just take this single the half cell and then find the electrode potential, because it is an incomplete arrangement. So, therefore, if I want to measure the electrode potential of different electrodes, I have to connect it to another electrode whose electrode potential is known. You know the electrode potential of that particular electrode, and then you find out the EMF of the cell by potentiometry. So, you know the two values for the in the equation where you have the electrode potential of the cell, EMF of the cell, and you have the EMF electrode potential of one of the electrodes is known. So, therefore, that with that in mind, let us discuss how to determine the standard electrode potentials of different electrodes. So, when you want to measure the electrode potential of zinc, now I will have to, what is the equation we are going to use here? The equation what we are going to use here is E cell is going to be equal to E cathode, or E naught cell is equal to E naught of cathode minus E naught of anode. So, this will become the standard EMF of the cell, standard EMF of the cell. So, the EMF of the cell, what is a cell? A cell comprises of the anode and the cathode. So, if I know the EMF of the cell, which you can measure it by potentiometry, then I will know the EMF of either the anode or the cathode, then you can calculate the electrode potential of the other electrode. So, those electrodes whose potential is known, you call them as the standard electrodes, and one such standard electrode is the standard hydrogen electrode, is the standard hydrogen electrode. The standard hydrogen electrode, which is also called as She, also called as She. So, let us draw the diagram for the She electrode. Now, this is the setup for, this is the construction of the standard hydrogen electrode. So, in the, you can see that this electrode is made up of two glass tube, the inner glass tube and the outer glass tube. Now, to the inner glass tube you have the platinum wire, and to the one end of the platinum wire you have a thin platinum foil which is coated with platinum, and this copper wire forms the external contact, and then to the inner tube it is covered by an external outer tube, and then that outer tube has an inlet through which hydrogen gas can be passed. Now, this electrode is dipped into a solution of HCl, which has a molarity of 1 molar, So, this electrode is called as the standard hydrogen electrode. How does this standard hydrogen electrode work? Now, when the hydrogen gas is passed through the outer tube at 1 atmospheric pressure, it passes through the tube and comes in contact with this platinum foil. So, on the platinum foil the hydrogen atoms get absorbed, So, it looks as if H2 is in contact with the hydrogen ions which are present in solution. So, what is the reaction which is occurring at the electrode, and the temperature is maintained as 25 degrees centigrade. The reaction which is occurring here is half H2 plus E minus, and it is a reversible reaction. These are the two giving H plus E minus. This is the reaction which is occurring. If you see, I have put a reversible sign here. Now, the reason for me to put the reversible sign is that depending upon the nature of the metal with which this standard hydrogen electrode is going to be coupled with, hydrogen electrode can act like an anode or it will act like a cathode. If I couple it with zinc, because of the nature of zinc, oxidation occurs at zinc and hydrogen ions get reduced, or in other words, zinc will act like the anode and hydrogen is going to act like the cathode. So, if I find out the EMF of, so this is the zinc electrode, I couple it with the standard hydrogen electrode, then this reaction is going to occur at the zinc electrode, and because this is cathode, this reaction is going to occur, H plus E minus giving half H2. Reduction is going to occur. So, therefore, the standard hydrogen electrode is going to act like the cathode, and if I measure the EMF of the cell, the EMF of the cell is found to be 0.34 volts, will be equal to, cathode is going to be, cathode is not 0.34, sorry, is 0.76 is going to be equal to cathode standard hydrogen electrode, it is taken as 0. So, E naught of H plus bar H half H2 is 0.0 volts minus E naught of Zn 2 plus bar Zn. or E naught of Zn2 plus bar Zn is going to be equal to minus 0.76 volts. So, if I couple it with a more electropositive element, then it is going to be this, it will act like a cathode, it will act like a cathode. But on the other hand, if I couple it with copper, if you couple it with copper, then at the copper you will have reduction taking place 2 plus, and oxidation occurs at the standard hydrogen electrode. So, this reaction is going to occur. So, this reaction is going to occur. So, again you can calculate the standard electrode potential of copper. So, for that we again make use of this equation. E naught of cell is going to be, is found to be 0.34, which is going to be equal to E naught of cathode, that is your copper, which is Cu2 plus bar Cu minus E naught of hydrogen electrode, half H2. So, for this the value is 0. So, E naught of Cu2 plus bar Cu minus 0 or E naught of Cu2 plus bar Cu is going to be equal to plus 0.34 volts. It is going to be equal to 0.34 volts. So, this is how you can determine the EMF of different electrodes. Now, why this is occurring, why this reaction occurs at when why hydrogen acts as a anode when coupled with zinc, and why it acts like a cathode, when it is coupled with zinc, then it depends on the nature of the metal here. Now, these electrode potentials, since they are measured at concentration of 1 molar and at 25 degrees centigrade, we call these electrode potentials as the standard electrode potentials, which is E naught, Now, these standard electrode potentials are arranged in an increasing order. The standard electrode potentials or the standard reduction potentials of the various elements are arranged in an increasing order, and that arrangement is called as the electrochemical series. It is called as the electrochemical series. It is called as the electrochemical series. Now, in the series, lithium occupies the topmost position, while fluorine occupies the bottommost position in the series. Because it occupies at the topmost position of the series, it is a good reducing agent. The value is going to be a negative value. The values is going to be negative, while as we go down the series, the values, if I say it is increasing, it is going to become more and more positive. It becomes more and more positive. So, if they are going to be more and more positive, then they are going to act like oxidizing agents. If they become positive, it acts like a oxidizing agent. So, the elements which are placed above hydrogen in the electrochemical series, they are good reducing agents, while those which are placed below hydrogen in the electrochemical series, they are good oxidizing agents. Now, the electrochemical series can be used to determine the electronegative character or the reducing power or the electropositive character or the oxidizing power. So, all these can be obtained by knowing the standard electrode potential. So, let us see how you can apply the electrochemical series to determine the electronegative character, the oxidizing power, the oxidizing power. So, let us see here fluorine, the E naught value of F is plus 2.87 volts. For chlorine, the E naught value, so let me write it here, the element E naught reduction potential is fluorine, chlorine, bromine and iodine. This is plus 2.87 plus 1.36, this is plus 1.06. For iodine, it is 0.57, all of them in voltage, volts. Now, you see these values. So, among these 4 elements, fluorine has the highest value for its reduction potential, or in other words, it has the highest or the more positive value for the reduction potential. So, if the reduction potential is positive, it means that it has a greater tendency to accept electrons. So, if it has a greater tendency to accept electrons, then the other element will have the greater tendency to give the electrons, or in other words, fluorine is oxidizing the other element. So, greater the value of the standard reduction potential or more positive the value of the standard reduction potential, more negative is the element and greater is the oxidizing power. So, when you arrange these elements in the decreasing order of oxidizing power, it has to be fluorine greater than chlorine, which is greater than bromine, which is greater than iodine, or in other words, the least iodine has the least oxidizing power. And the second application where you can apply this electrochemical series is to determine the electropositive character or its reducing power, So, let us compare the elements here. So, element and then the reduction potential E naught values for sodium, magnesium, aluminum, zinc. So, for sodium it is plus 2.7 minus 2.71 plus minus 2.37 minus 1.66, this is minus 0.76 volts, 6 volts. So, here if you see all of them have the negative values. So, that means these elements are not capable of accepting electrons, rather they can give electrons, or in other words their electropositive character is more, that means they can get converted into positive ions easily. So, and also because they are capable of losing the electrons more easily than accepting it, they act like reducing agents. So, more negative the value for the reduction potential, greater is the electropositive character and greater is the reducing power. So, how will the reducing power change here among these elements? It is going to decrease in the order sodium greater than magnesium, which is greater than aluminum, which is greater than zinc. So, this is another application of your electrochemical series. Now, this electrochemical, the third application is to calculate the EMF of the cell. You can use this electrochemical series to determine the EMF of the cell, that is E cell. Now, E cell is given by the equation E of cathode and E of minus E of anode. So, from the electrochemical series or the values of the E naught values, you can determine which element will act like the cathode and which metal will act like the anode. Let us compare our known example, which is copper. Copper, the E naught value for the standard reduction potential for copper is 0 plus 0.34 volts, and E naught value for zinc, that is zinc electrode, it is Zn 2 plus bar Zn, this is going to be minus 0.76 volts, 0.76 volts. So, if you want to determine which will act like the cathode and which is going to act like the anode, we need to go back to our definition. What does the definition say? Cathode is the electrode at which reduction takes place, and anode is the electrode at which oxidation is going to take place. Therefore, here if you compare the electrode potentials of copper and zinc, for copper it is more positive value as compared to that of zinc. Therefore, definitely reduction is going to occur at copper, or it has a greater tendency to get reduced because its E naught value is positive, while the E naught value of zinc has a greater tendency to get oxidized. The reason being its electrode potential is negative. So, copper will act like the cathode, more positive the value for the electrode potential, the metal will act like a cathode, and more negative the value for the standard reduction potential, the metal will act like the anode, So, this is the third application for the electrochemical series. Sir, ಎಷ್ಟಾಯಿತು ಟೈಮು? ಈಗ so the next application for the electrochemical series is to see whether a metal can displace, which metal can displace, if the metal can displace hydrogen gas from dilute acids, from dilute acids. Now, let us take HCl, dilute HCl. So, in that we have H plus ions, and let us take sodium. So, if sodium has to displace hydrogen from the solution, then the following reaction must occur. The following two reactions should be able to occur. That is, sodium, if hydrogen gas has to be liberated, hydrogen ions must get reduced to H, or we can put this as 2H plus 2E minus, giving H2. And where do we get the electrons from? The sodium metal must be capable of giving the electrons to hydrogen. Now, let us take copper. So, if I place copper in dilute acid, then this reaction must occur, 2 plus 2E minus. Now, let us see which of the two metals is capable of displacing hydrogen from dilute acid. So, for this case we need to look into the E naught value. So, the standard reduction potential of sodium, okay, let me write it on the other side. The standard reduction potential of sodium Na, it is minus 2.71, and E naught of Cu2 plus bar Cu is going to be plus 0.34, and E naught of hydrogen is 0, as we know. So, in this case, when you compare the standard reduction potential, E naught of sodium is more negative than compared to hydrogen. So, therefore, sodium is capable of getting oxidized. So, it can give the electrons, and the electrons can be used to reduce the hydrogen. So, since the value of E naught standard reduction potential of sodium is lesser than that of zinc, or it is more negative than of hydrogen, lesser than that of hydrogen, and it is more negative as compared to that of hydrogen, the following reaction can take place, and it can displace hydrogen gas from a dilute acid solution. But in the case of copper, the E naught value for copper is positive, that means it is more than that of hydrogen. So, hydrogen is only capable of giving electrons to copper, but it cannot accept the electrons from copper, because copper cannot give the electrons because of its more value. It has a higher value for the reduction potential as compared to hydrogen. So, copper cannot displace hydrogen from a dilute acid, while sodium can displace hydrogen from dilute acids. Can displace hydrogen, cannot displace hydrogen. Or in other words, in a more easier way, the elements which are placed below hydrogen in the electrochemical series cannot displace hydrogen from dilute acids, while the elements which are placed above hydrogen in the electrochemical series can displace hydrogen from dilute acids. So, these are the four important applications of the electrochemical series. Now, this same concept can be applied to determine whether a metal can displace another metal from its solution. Okay. So, but the most important ones are these 4 applications. And also the other application is from the EMF of the cell, you can, from the EMF of the cell, you can determine the equilibrium constant and also the delta G value or the Gibbs free energy for the particular reaction. So, the next part what we are going to talk about is the factors. So, now we have learnt what are the concepts we have learnt here. We have learnt what is a galvanic cell, what are the 2 types of electrodes, the anode and the cathode, what are the reactions which occur at the anode and which occur at the cathode, how the electrode potentials are developed at the positive electrode and at the negative electrode, and then we have learnt about how you can determine the standard electrode potentials by using the standard hydrogen electrode, and we have learnt what is meant by electrochemical series, what is chemical series, and also the applications of the electrochemical series. So, the next part here is what are the factors affecting, what are the factors affecting the electrode potential. What are the factors affecting the electrode potential? The first factor which affects electrode potential is temperature. The reason being, here the electrode potential depends upon the concentration of the ions, and we are taking the concentration of the ions in molarity, and we know molarity is dependent on temperature. Then B, it is dependent on the nature of the metal, C, the concentration of the metal ions, and D, concentration of the metal ions, and D, the valency of the metal ions or the charge on the metal ions. These are the 4 factors which affect the electrode potential. Rather, we can write this as molar concentration. That would be more appropriate for us to write it as the molar concentration. So, these are the factors which affect the electrode potential, and an equation is there which relates the EMF of the electrode potential to all these factors, and that equation is called as the Nernst equation. Nernst gave an equation which gave a relationship between the electrode potential, temperature, the concentration of the ions, and that equation is known as the Nernst equation. Nernst equation. So, now let us derive the Nernst equation. Consider an electrode where the following reaction occurs. Mn plus Ne minus giving metal. This is a general equation. So, according to Nernst equation, E of the electrode, okay, the single electrode potential, which is Mn plus bar Mn, is going to be equal to E naught of, that is the standard reduction potential of the electrode, Mn plus bar M minus 2.303 RT by Nf into log of concentration of the metal divided by concentration of the metal ions. Now, the metal ions are in aqueous medium and this is a solid. So, concentration of the metal, the solid state, concentration of the metal ions in aqueous medium. The concentration of metal solid is taken as unity, because we know that the concentration of the solids changes hardly with So, therefore, this equation can be written as E naught of M n plus bar M minus 2.303 RT divided by Nf into log of 1 by M n concentration of the metal ions in solution, concentration of metal ions in solution. Therefore, this equation relates the electrode potential of the metal electrode with the concentration of the metal ions. Therefore, this is the Nernst equation for a single electrode, and this is an important equation. And what do the terms here stand for? E naught is the standard reduction potential of the metal electrode, R is the universal gas constant, T is the temperature, N is the number of electrons involved in this reduction, F is the Faraday constant, which and concentration of the metal ions in solution. Now, let us derive the Nernst equation for the EMF of a Daniell cell. So, what does this Daniell cell made up of? The Daniell cell is made up of a zinc anode, where the concentration of the metal ions is 1 and is a solid separated by a salt bridge, and where copper electrode is the cathode. So, zinc is the anode and copper is the cathode. This is the Nernst equation, this is the general representation of a Daniell cell. So, let us derive the Nernst equation for the Daniell cell. Now, so if we change the concentration of the Zn2 plus ions, then the EMF of the Daniell cell is also going to change. So, let us look into that equation here. So, we will remove this concentration as 1 molar. So, we know that EMF of a cell is equal to E of cathode minus E of anode. EMF of the cell is equal to E of cathode minus E of anode. So, in this case, since copper is the cathode, it will be E of copper electrode minus the standard reduction potential of the anode, which is the zinc electrode, The EMF of the copper electrode, according to Nernst equation for the single electrode potential will be equal to E naught of copper, which is the standard reduction potential of the copper electrode, minus 2.303 RT by NF into log of 1 by the concentration of copper ions in solution. Copper ions in solution. Similarly, E of zinc electrode will be equal to E naught of zinc electrode, which is the standard reduction potential of zinc electrode, minus 2.303 RT by NF into log of 1 by Zn 2 plus ion concentration of that particular Daniell cell. So, therefore, we need to derive the EMF of this cell here. So, what is the EMF of the cell going to be equal to? EMF of the cell will now be equal to E cell. Okay? E cell will be equal to E naught of Cu2 plus bar Cu minus 2.303 RT by NF into log of 1 by Cu2 plus minus of that of zinc, which will be equal to E naught of Zn2 plus bar Zn minus of minus will become plus 2.303 RT by NF into log of 1 by Zn2 plus. But we know that E naught of Cu2 plus minus E naught of Zn2 plus is going to be equal to the standard EMF of the cell, which is E naught of cell minus 2.303 RT by NF into log of 1 by Cu2 plus 2.303 RT by NF into log of 1 by concentration of Zn2 plus. This I can take out the common terms here, which is minus 2.303 RT by NF. So, the equation will become E naught of cell minus 2.303 RT by, it will be equal to E naught of cell minus 2.303 RT by NF into log of, if I take out minus here, this will also become minus. So, the concentration of, you can have, write it as Zn2 plus divided by copper Cu2 plus of copper 2 plus. So, this is the Nernst equation for any Daniell cell, for any Daniell cell. Suppose, so for a general, therefore, for any general electrochemical reaction, we can give the Nernst equation as follows. Let us consider an electrochemical equation here, where A of A plus B of B giving C of C plus D of D. It is the electrochemical equation. So, this will be the cell reaction, or we will write this as cell reaction. Let us give the Nernst equation for a general electrochemical reaction, which is as follows: A of A plus B of B giving C of C plus D of D. So, E cell will be equal to E naught of cell minus 2.303 RT by NF into log of concentration of C to the power C D to the power D divided by concentration of A to the power A into concentration of B to the power B. So, this is the general Nernst equation for a electrochemical reaction. Now, suppose let us take a more general example here. Suppose we have a Daniell cell which has the anode metal M giving M1 plus, okay, separated by a salt bridge, and a cathode M2 N plus bar M2. Then the Nernst equation for this will be E cell will be equal to E naught of cell minus 2.303 RT by NF into log of concentration of M1 N plus divided by concentration of M2 N plus. Or in more general terms, this I can write it as E naught of cell minus 2.303 RT by NF into log of concentration of product divided by concentration of reactant.